walk you through beta and estimating beta. So this is a statistic that you often see reported with financial data, and it's just an application of regression. So we use regression to estimate the beta. So in your other classes, in some of your other finance classes, you may have covered the concept. We'll think about how to actually estimate beta using data that you can collect yourself. So we always go back to risk, and risk is just uncertainty. So uncertainty about the future value is what we consider risk. So if you had perfect information about the highs, the lows, the ups, the downs, there would be no risk because you could always plan for that. You could always take action, make a trade, do something to avoid any type of negative return. But we don't know the future, so there is always some form of risk. There are various types of risk. So there's market conditions, industry conditions, the company itself. So risk can come from a number of different levels. So it can come from things that are going to affect everyone in the market. There are things that affect particular industries. There are things that affect particular companies. Some of these things we'll see later can be diversified away. Some of them cannot be diversified away. What we are really going to be interested in this section is the market conditions and how things move with the market. So we can have two things that look very similar, but one is highly correlated with market returns. One is not going to be as correlated with market returns. And that's what we're going to think about more with beta. In what we have done so far, and the statistics that we have, or the sample statistics that we've been estimating, the standard deviation is our most common measure of risk because that standard deviation tells us how something deviates around the mean. So if you know the mean for something, so you know the average value, that's useful information. But we want to know, do we expect the values to be close to that average, or do we expect values to be far from that average? Now, for example, let's say we have returns and they both have an average of 5%, and one of them returned 5% 3 months in a row. So 5%, 5%, 5%. That's going to give an average of 5%. Well, let's say the other one was 2%, 5%, 7%. Well, the average of those is still going to be 5%. Or maybe I messed the math up there. But as long as the average works out to be 5, you can have some below 5, some above 5, but we still average 5. One will have standard deviation, one has no standard deviation. So that's information that we want to consider when we're looking at returns. So if we're thinking about market risk versus idiosyncratic, and this is just another word for random. So it's just an academic word that we use for random for no real reason. So market risk describes a type of risk that's going to impact all firms in a market. So you can't diversify this away since everything's going to be affected. So let's say an asteroid hits Earth. That's going to affect everybody. That's going to affect everything. You can't diversify that away. Just because you're Tesla or because you're Microsoft doesn't mean the asteroid hitting the Earth isn't going to affect you. So this is going to affect everything. More reasonable examples of this would be the financial crisis, the pandemic. A lot of these things affected just about everything. Now, some industries did better. Some industries did worse during the pandemic. Some things not everything was affected in precisely the same way, but these are things that have market-wide consequences. Random risk or idiosyncratic risk that can be firm or stock-specific can be diversified away. So let's say there's something that could affect a particular industry. Well, you can diversify that away by building a portfolio with multiple industries. So if everything's in automotive, and there's something that affects the automotive industry, well, everything in your portfolio is going to be affected. But let's say there's something that's only affecting the automotive industry, but you have some automotive, you have some mining, you have some real estate, you have various different sectors in your portfolio, then you can diversify away some of the risk in the automotive sector by including things from other sectors as well. So this type of risk can be diversified away through selecting by carefully building a portfolio. Market risk is going to affect everything. So everything in the portfolio will be affected in some way. We saw this with chip shortages several years ago, especially for new vehicle manufacturers. I think it was the Ford plant that had a lot of vehicles built waiting on one part. So they had hundreds and hundreds and hundreds of vehicles that couldn't be sold because they were waiting on one part. Well, if you were making toasters, you probably didn't. That chip shortage may have not affected what you were doing, or if you were logging, probably didn't affect you that much. There's some trade restrictions. So if we have an industry that's heavily dependent on steel, and steel has to be imported in a particular location, well, if they can't get the steel, then it's going to affect that sector. But maybe the sector that relies on grain or something else is not going to be affected. So these are more firm industry specific types of risk. So this goes back to what we were thinking earlier, just looking at risk and volatility and using standard deviation as a measure of risk. So all three of these have an average return of 1% a year. So on average, we're getting 1% per year. Again, this is compounded. I know it looks fairly linear, but it's not perfectly linear. So we're getting a 1% return every year. The red line has a standard deviation of 0, so they get 1% every year. The green line has a standard deviation of 1%, so it's a return of 1% with a standard deviation of 1%. So sometimes it's higher, sometimes it's lower. So notice we see some deviations around that line. And the blue one has a standard deviation of 3%. So notice we see more variation around the line, but sometimes it's high, sometimes it's lower, but on average we're getting 1%. And that's how we see it. We see this volatility. Sometimes it returns higher, sometimes it returns lower. So if you're thinking about these, which one would you want? I'm going to choose the one with the standard deviation of 0%. If I'm going to get a 1% return on average, I'm going to choose that 1% with 0 standard deviation. Now, what's a little bit different is, let's say you can have 1% with no standard deviation or 2% with some variance. Now it's not as obvious which one you want to choose, depends on your goals. But if all three have a 1% return, then, and if you're going to be in this possibly in a shorter term or something, I'm going to take the one with the lowest risk. Now, at the end of the 50-year time period, notice they all ended up about the same. So we see more and more volatility around the line down here in these lower years. At the end of 50 years, if you ran this experiment over and over and over and over again, they all would average 1%. But most people are going to go with the one with the lowest amount of risk for the same level of return. And later, that's an assumption we will actually make. So another example here, looking at standard deviation and return, we have two things, both with a mean of 2% and a standard deviation of 2%. So both of these, they look identical. They have the same standard deviation, they have the same average return, but they are going to be very different. So even though they look identical, when we compare those to the market return, they look very different. So notice the market return down here. So we're always going to use the S&P 500 as our market return. So if you look at this, we have the market return could be positive or negative, and the stock return could be positive or negative. If you look at stock 1, there's no correlation between the return on that stock and the return in the market. So when the market's up, the stock might be up, it might be down. When the market's down, the stock might be up, it might be down. And compare that to the one on the right, where on average, when the market is up, so is the stock. And when the stock is down, and when the market is down, so is the stock. And if you're thinking about regression, which is the section we just finished, if you think about estimating a regression using this data right on the left, you're probably going to get a big fat 0 for your slope. The line would be flat and would go right through the middle of that data. If you ran a regression on the right side here, the slope would be positive because the market returns has a positive correlation with the stock return. So the slope of the line that we estimate through a plot like this is how we estimate beta. Now this is using market returns and stock returns, where what we want to use when we estimate beta is actually the risk premium for the market and the risk premium for the stock, which is just excess returns above and beyond the risk-free rate. But that's all we're thinking about with estimating beta. and how it compares to the market. And if we know how well it correlates with the market, we'll know how much of this risk can be diversified away and how much cannot be diversified away. So looking back at it, looking at the same two things again, we're going to say stock one, these returns are independent from the market, while stock two are going to be, I'm not going to say dependent on the market, but highly correlated with market returns. So I'm not going to say that the market return is what's causing the stock return, but they are highly correlated with each other. Right? And we're going to use regression to estimate that relationship. So a little bit of terminology before we get to the regression. So the risk-free rate is going to be the return on a risk-free investment. So we're going to use treasury bills. So the bonds that we can buy from the government that are backed by the full faith that are backed by the government. I can't remember exactly what they say, by the full faith and something of the federal government. So we're assuming there's no risk of default. Is there always some risk of default? Yes. Is it low enough we can just call it zero? Basically, is what we're doing here. So the risk-free rate is the return on a risk-free investment. The market return, we are going to use the S&P 500. You can use some index. There may be some, you could use a different index, but we're going to use the S&P 500. I think that's pretty standard when we're estimating beta. The stock return is just a return for a particular stock. We've looked at this over and over again this semester. So you have to take the prices, convert it to returns first, because we don't want to work with prices here. We want to work with returns. The risk premium is the market risk premium is just the market return minus the risk-free rate. So let's say the risk-free rate's paying 4%. The market return was 8%. That risk premium would be 4%. The 8% market return minus the 4% risk-free return. Same thing for the stock risk premium. We're going to estimate the stock's return, compare that to the risk-free rate. So if the risk-free rate is 4%, but the stock return 2%, the risk premium is actually negative in that case. If the stock return was 4%, it would be 0. If it was above 4%, the stock risk premium would be positive. So we want to know how well is the stock in the market doing relative to a risk-free, some risk-free asset or investment. So this is the regression that we're going to use to relate the market returns, the stock returns to the market returns. So the dependent variable is going to be the risk premium for the stock, and the independent variable will be the risk premium for the market. So this is a simple regression with only one independent variable. So once you estimate your market risk premium, that's going to be your independent variable. And then the dependent variable would be the risk premium for the stock. And this is the beta for the stock. So alpha is the intercept, beta is the slope, and then epsilon is the error term. So those are all the determinants of the stock's risk premium, except for the market. So this is going to tell us how sensitive it is to the market return. So if go back to our basic regression examples. If the estimated coefficient is positive, then it means the slope is positive. So that means the stock is more volatile than the market. So if the market risk premium if increases, we would expect the stock to increase by even more than that. Again, we're comparing this to 1, not just positive or negative. So if it's greater than 1, it's more volatile than the market. If it's less than 1, it's less volatile than the market, because if the market risk premium increases, the stock will increase, but the stock risk premium will go up, but by less than the market risk premium. And then 0, it moves in the opposite direction as the market. So if you have some stock that's moving, the risk premium is increasing while the market risk premium is negative, is going down, then they're moving in opposite directions. Then equal to 1 would be the market risk premium. The stock risk premium moved proportionally to the market risk premium. So if you think about an index fund like the SPY, I think, or like the S&P, like some kind of S&P 500 index fund, it's going to have a beta of 1 because it's designed to move with the market. So if the market's up 5%, that index will be up 5%. So that's how you would get a beta of exactly 1. So R-square is also something we think about with estimating beta. We thought about it with regression. It's also going to show up here. So it's the amount of the variation in a firm's risk premium that's explained by the market risk premium. So if you go back to the just basic definition of R square, it's the amount of it's the variation in the dependent variable explained by the independent variable, or independent variables if you have more than one. The dependent variable is the firm's risk premium or the stock risk premium, and the independent variable is the market risk premium. So it's the amount of the variation in the firm or stock risk premium that's explained by the market risk premium. Same definition, just different context. And that's the amount of risk that's due to the market, and it cannot be diversified away. So if you regress a firm's risk premium on the market risk premium, and you end up with an R square of 0.8, well, it says 80% of the variation in that firm's risk premium can be explained by market conditions. So only the remaining 20% can be diversified away. So 1 minus that R square is the amount that's not explained by the market, and that can be diversified away because that's firm or industry specific risk. But then epsilon is this just randomness. So there's always going to be some randomness in the risk premium for a particular stock, and that's going to capture that. So those are all the determinants of the firm risk premium that are not in addition to the market. So once you've held constant the market risk premium, those other factors that are explaining the variation in the firm's risk premium, that's what's captured by epsilon. It's all of those other determinants. Again, alpha is the risk premium when the market risk premium is 0. So again, that's the definition of the intercept. So if we let the market risk premium equal 0, we're left with just alpha. Again, we assume on average that epsilon would be 0. So when the market risk premium is 0, alpha is what's left. So that would be the firm's risk premium when the market risk premium is 0. And then theory says that that should be 0. So if you're looking at Excel data and how we actually do this, so we have the market and the stock returns right here, and then the risk-free rate. This will all be given to you. So you'll be given the market return, stock returns, risk-free rate. The market risk premium, so this column F, is just this market return minus the risk-free rate. Right? So if you take negative 0.34 and you subtract 0.83, again, when you subtract here, we're actually, so this is a negative minus a positive. So we get an even bigger negative number right here. So this negative 1.17. So that's just the market return minus the risk-free rate. The same thing for the stock 1 return. So take the stock 3.91, subtract the 0.83. That gives you your 3.08. So these stock risk premiums are just the differences between the market or stock returns and the risk-free rate. And here's another slide just with the formula so you can see exactly how that's working. So if we're going to compare two stocks here, this is very similar to what we had earlier, except what we have now is the risk premium. So let me scroll back up here to the top. What we were doing here, we had the market returns and the stock returns. What we were doing now when we actually estimate beta is we have to do the risk premiums. So what we're doing now is looking at the difference between the stock risk premium and the market stock risk premium and the risk-free, market risk premium and risk-free, and that's what we're using to estimate the regression. So when you have some relationship like this where the market and the stock returns are completely uncorrelated with each other, you're going to get a beta of 0 and an R square of 0, which says information about what's going on in the market tells you nothing about what's going on with that particular stock. And this other example where they're highly correlated with each other, we're getting an R square of 0.81 and a beta of 1.79, which tells us if the market risk premium increases by 1, the stock risk premium will increase by 1.79. So the risk premium is actually moving in the same direction, but it's moving more than the market risk premium. So if you think about what that 1.79 represents, it's the slope of the line that we estimated through those points. So if you look at the slope of this line right here, it would be exactly 1.79. So, and that 0.81 tells us that 81% of the variation in the market risk premium, 81% of the stock 2 risk premium is explained by the market risk premium, The other 19% is explained by other factors. So market risk premium is up by 1%. The stock risk premium is up 1.79%. So it's more volatile. That also works in the negative direction. So if the market risk premium decreases by 1%, the stock risk premium will decrease by 1.79%. So it moves more in the positive direction and in the negative direction. When we're looking at the regression output, when we look at this the same way we would think about any regression output, this is our intercept, so that's the estimate of alpha. Again, it's statistically different from zero. This is a made-up example, so this is just generated data, so don't get too worked up about that. And then this is the coefficient for beta. Our estimate was actually negative 0.02, but notice that p-value is really, really high. That is not statistically different from zero. So we're saying here the market risk premium is zero. The confidence interval is negative 0.59 to 0.56. So we failed to reject the null hypothesis that the market risk premium, that the beta is equal to zero here. And our R-square is also zero, which means there's zero correlation between the market risk premium and stock 1. For stock 2, here's the R-square. So 81% of the stock risk premium is explained by the market risk premium. Here's our estimate of the of beta, 1.79. P-value is 0 to 2 decimal places. So we reject the null hypothesis that beta equals 0 in this example. Again, this is your estimate of alpha. It's statistically different from 0. Again, this is hypothetical data, so don't worry about that. So here's some real data. So this is going back to 2015, so it's a little bit older. And I used 5 years of data here. What you typically see, like on Yahoo Finance or something, would be usually a 5-year beta. That's what you typically see. So here's the risk-free rate, the Tesla return, Microsoft return, SPY. So this is what we're using for the market, and then GE. So here are your risk premiums. And here are the regressions. So if you look at Microsoft here, we estimated a beta of 0.91 and an R-square of 0.45. It is statistically different from 0. Again, your alpha is also statistically different from 0, but we don't care about alpha right now. We're only interested in estimating the beta. So using 71 observations, we estimated a beta of 0.91 for Microsoft with an R-square of 0.45. And this is what it looks like if you plot it. So if you plot the Microsoft risk premium against the market risk premium, we see a positive slope. And the slope of that line is exactly 0.91. For Tesla, the beta was 1.88 with an R-square of 0.21. So the market risk premium explains less of the variation in Tesla risk premium than it did for Microsoft. And Tesla is also more volatile. So if the stock risk premium increases by 1, Tesla's risk premium is 1.88, so more volatile than the market, but it's not explained very much by the market. So only 21% of the variation in Tesla is explained by variation in the market risk premium. The other 79% is explained by other factors, firm or industry specific. And here's the plot. Again, these are on different scales, so it's hard to... Actually, let's see, we're going from about negative 20 to 20 there. Let's see, are the scales that much different? Yeah, our vertical axis is a lot different here. So notice we're going from negative 10 to 20 here, and we're going from negative 25 to 75 here. That's why it may look flatter, but it actually has a steeper slope than it does for Microsoft. And this is General Electric. Again, we get a beta of 1.09. It has the same R-square as the Tesla regression. So what's going on with General Electric? Not explained a lot by the market risk premium, but the beta is closer to 1 here. So it's a little more volatile than the market, but not a lot more volatile. And p-value is 0, so it is statistically different from 0. And then this is what it looks like if you plot it. So this is the market risk premium, GE risk premium, and the slope of the line that goes through those points would be your beta of 1.09. And that's it for beta. It's relatively straightforward. If you can estimate regression, you can estimate beta. You have to have the data to do it. But again, that's not an incredibly difficult thing to get. A place like Yahoo Finance makes it a little bit harder to get data now, but you could go pull data from different sources um, and look up the beta for a particular stock. So I'm just going to pull one up real quick here on Yahoo Finance. Just show you where that beta actually is. So here is, I just pulled up Tesla. So this is on Yahoo Finance. And you'll see right here, here's your, actually it's not giving you the beta, which is interesting. Let me look up something else here. Let's just look up General Electric. There we go. So there's our beta. Our 5-year monthly beta for GE is 1.39. So that's the number that we are actually going to be estimating here. The way you would do this using data like this, you go to your historical data. And this is where you could actually pull. So you could actually pull historical prices monthly. Let's just go 5 years. This is the type of data that you would be using to estimate your beta. So you would have to also go find the risk-free rates at the same time periods, but that's it. If you can pull the price data, use that to generate your returns, and then get your risk-free rate, you could estimate beta, and then you could try to estimate something and see how close you get to the actual beta that we're seeing right here.